Good afternoon. I'm Peter Goddard, Director of the Institute for Advanced Study, and it's my pleasure to welcome you to this, the first of 4 weekends throughout 2005, when we'll be celebrating the 75th anniversary of the founding of the Institute. The founding act, the signing of the Certificate of Incorporation, took place on May the 20th, 1930. And on Friday, May the 20th this year, we shall have a general celebration which marks the centenary as well of Einstein's Annus Mirabilis, which everybody around the world is celebrating this year. The 4 weekends that we've planned focus on the work of our 4 schools. The order we've taken is historical, starting with the first school, mathematics. The School of Mathematics of the Institute began its life in September 1933 in the old fine hall of Princeton University. George Dyson will tell us more of those early days at 6:30 this afternoon. The Institute, it seems, immediately assumed a structure that those of us who were members in later years would recognize. Abraham Flexner, the founding director, wrote to a trustee, "What has happened is not exactly what I planned, but is much better than I planned. What has happened is the following. We have 5 mathematicians of great eminence, each with his own work to do. We've admitted to the Institute about 20 persons who have shown capacity for independent work. They have been turned loose in Fine Hall without any regulations whatsoever." And immediately, tea assumed a central role in the life of the community. He wrote, "Every afternoon tea is served informally, and there is, to my astonishment, an attendance of about 60. They talk about mathematics, but not only mathematics, and drift in and out without explanation or ascertainable reason." Well, it's not only the social customs of the school that were set early and have remained little changed. The school's leading place in the world of mathematics was quickly established, and the unique roles played in the development of mathematicians and mathematics internationally were set early. I'm delighted that so many of you, many from far afield, have come here to celebrate the achievements and continuing work of the Institute and its School of Mathematics. And now I hand over to Bob Langlands, Professor in the School of Mathematics since 1972, to introduce this afternoon's programme.
Let me begin by just making 2 very brief announcements. When I arrived, the 2 speakers were having a lively discussion as to which of them was the most handsome and which the most intelligent. I said we would put it to a voice vote at the end of the second lecture. Now, both speakers have agreed to take questions at the end of their lectures. So if something occurs to you, if something you don't understand, if there's something you need answered during the course of either one or the other lecture, try to remember it until the end and then pose the question. Now, our first speaker is Peter Sarnak. And I think I could say that if this were an audience that consisted entirely of mathematicians, he would need no introduction. But I have to assume that since some of you aren't mathematicians, a brief introduction is necessary. As you'll hear, almost immediately that he begins to talk, he was born and grew up in South Africa, in Johannesburg. He went to, he was undergraduate at the University of Witwatersrand, and then he went on to take a PhD at Stanford. Since 1991, he's been a professor at Princeton University. He's also been a frequent visitor here at the Institute. He's, of course, won quite a large number of prizes. I just want to mention 2, namely the Cole Prize of the AMS this year and the Polly Prize of the Society for the Industrial and Applied Mathematics. I mention the second because it illustrates one feature of Peter Sarnak's mathematical style, namely he's very wide-ranging, so it is significant that it's the Society for Industrial and Applied Mathematics that awarded him that particular prize. If you look at his bibliography, you'll see that he's contributed to many domains. The Cole Prize of AMS I mentioned because I was present when he received it, and I was struck by the generosity with which he acknowledged the work of his colleagues and co-authors in his response to the award of the prize. And it is, I think, a characteristic of Peter that he's very generous in many ways with his ideas. He's had a large number of students, some of them extremely good, and also he's very receptive to the ideas of others. Because of his generosity in the reception of ideas, because of his wide range of knowledge, it's always a pleasure to talk with him, and that's why so many people know him. And, but I think that's all I need to say. I'd like him to begin now. The title of his talk is Number Theory, Symmetry, and Zeta Functions.
Well, thank you for the very kind introduction, and it's, of course, great. Is this working? I have a very loud voice anyway. I probably wouldn't need this. It's a great honor for me to give this lecture. It's actually an impossible task. My instructions were to talk about symmetry and number theory and work down here. I understood that primarily also to mean to highlight some of the works of some of the permanent members here who work in number theory. Now, I could take any one of them and spend the whole term and give a course on their work, or even just describing their achievements. So it's clearly impossible to do anything like that in the space of our last 10 minutes, 15 minutes. So what I decided to do was to take some theme, particular zeta functions, which quite interestingly has been a theme that almost anyone who's worked here at the Institute, at least amongst the permanent members, has touched on as one of the themes in their work. All the members and visitors, actually, many visitors have worked also in many, many different fields. So I'm not trying to talk about any specific achievement of any person, but rather just a theme that unifies, I think, a number of achievements. All right, I tested this, it worked before. I'll try not stand in the way. So I'm going to start with Ramanujan to tell the story. Ramanujan had a great knack of posing questions, probing questions, whose solution he couldn't find, but when the solutions were eventually found, they actually were really at the bottom of the real issues. So maybe not every question he raised was so interesting. I'm going to mention two that he raised in the period 1916, 1917, and they will be the theme of the talk, and they'll allow me to introduce the main players in this. All right. So the first question was concerned about quadratic forms. Let me make clear that I will water down things. Some of the things I'll say are not true. So experts don't jump up and down saying non-singular this or that. I'm going to just try and be as accurate as I can. And one really nice thing about number theory amongst the fields of mathematics is you can pose problems that everybody can immediately understand, and often the solutions are very different, very difficult. There's a very great difference between mathematicians and physicists. Physicists always try to tell you how simple what they're doing is, and mathematicians always will try to tell you how complicated what they're doing is. The real truth is somewhere in between, and number theory has this beautiful feature of having very simple problems and actually quite complicated proofs. So the problem he was considering, and I'll review the history of this in a second, was which numbers can be written as x1 squared plus x2 squared plus 10x3 squared. He put 10 there for a reason. You'll see it momentarily. And he asked which numbers, positive integers, can be written in that form. So which numbers are represented by that quadratic form, where everything here, the feature of number theory is everything here are whole numbers. He noted immediately that numbers of the form, say for lambda 0, they're lambda and mu are integers, numbers which give remainder 6 when divided by 16, something we'll be returning to in a second, are not represented. You cannot solve that for those numbers. He noted that as obvious, nor numbers which are the form 4 to the lambda times z. But then he noted, more interestingly, the following odd numbers, for which it's not much less clear from a certain perspective that I'll give you in a second, are also not represented, and he listed 16 of them. Later, these two numbers were found, and in fact, Galway, I think a graduate student maybe at Illinois a few years ago, checked that if you look at all numbers up to 2 times 10 to the 10, the only exceptions are on this list here, those that Ramanujan wrote down, and those two. I would like to say we know the answer to Ramanujan's question today. We still don't. Amazingly, we don't know that answer, but I'll return to that in a moment. The second question that he raised a year later, or maybe it was a year before, concerned something that looks a lot more obscure, perhaps, but for him this was a very important and for many people function to study. But Ramanujan, like Euler before him, liked to manipulate series, and especially with integer coefficients, as we'll see. So I'll ask you just to look at this expression for a second. You take q is a variable, or a symbol if you wish, times this infinite product to the power 24. And if you expand that out, say by the binomial expansion, one term at a time, collect terms, you'll see that for each power of q, there'll be infinitely many terms contributing, and you'll get these coefficients here. So for example, you'll get 1 in front of the q. You'll get minus 24 if you calculate in front of the q squared, and so on. And in fact, I photocopied his table here in his paper on the subject. He gave the numbers tau of n all the way up to 30, and they get quite big, as you can see. And then he makes two far-reaching observations which are crucial to this lecture. The first, he observes that if m and n have no common factors, like if you take tau of 2 and tau of 3 and then look at tau of 6, you'll see tau of 6 is tau of 2 times tau of 3. So if m and n have no common factors, then tau of mn is tau of m times tau of n. I think most people would have noticed that, actually. That doesn't take Ramanujan. The next thing, however, very few people at that time in 1916 would notice. He observes that at a prime number, so if you take 2 or 3 or any prime number, the absolute value of tau of p is at most twice p to the 11 over 2. It certainly takes a genius to see that that's of importance. He even writes it in this way, which for some reason will be appealing to us later. He writes this quadratic equation, 1 minus tau p times t plus p to the 11 times t squared. And the statement of this inequality, if you work out the roots of that equation, is the statement that the reciprocals of the roots are exactly of absolute value as complex numbers p to the 11 over 2, and he even remarks that. And he continues to remark that tau can't be smaller than p to the 11 over 2 for many p's, or n's at least, P is a little harder to prove, but ends. And so he highlights the importance of that exponent. He was quite interested in how big these numbers could be. So those were two actually very far-reaching insights of Ramanujan. Let me go back a moment and explain to you why his first question was not out of the blue. It was studied by many people. One of the earliest theorems in number theory, and one that you'll find in any elementary book, and is still a marvelous theorem even today. Every positive number is a sum of 4 squares. And that's the theorem of Lagrange. Of course, people immediately ask, well, which number is a sum of 3 squares? This is already quite a bit more difficult. You won't find it in every elementary book. In fact, you won't find it in most elementary books. And I want to immediately bring it to the fore of the theme. The theme is local to global in this lecture. So one way to see there's something different with sum of 3 squares is if we look at the remainders when you divide by 8, or from now on what I will call arithmetic modulo 8. So if I look at x, and I look at the possible remainders, they are 0, 1, 2, up to 7. And if I square that out, keeping only the remainder, I'll get 0 for 0 squared, 1 for 1 squared, 4 for 2 squared, 3 squared is 9, which is 1, and so on. So I'll only get these numbers for the squares. And if you look at that for a moment, you'll find that you can never write 7 as the sum of the 3 numbers in the second row over here in arithmetic modulo 8. So immediately any number which gives remainder 7 when divided by 8 will never be a sum of 3 squares, and we're on a different page. It's not like the sum of 4 squares. There's an obstruction. I'll call this a local congruential obstruction that anybody who thought about this would see more or less immediately. One can also show that any number of the form, not just giving remainder 7 modulo 8, but 4 to the a times 8b plus 7 will also not be expressible as a sum of 3 squares for the same reason. So there is this local obstruction, and what you would love is once you pass this obstruction, there's no more problems. And that was, I thought, a theorem of Legendre, but I prepared this lecture and found that it's actually due to Gauss. Actually, this seemed to be, I should have looked at Weil. He usually has the right answers on the history. But in any event, I'll give it the credit here to Gauss. Certainly, he proved this, that as long as you're not of this form, is content to the theorem, then you are a sum of 3 squares. So once you pass this local obstruction, then there always are 3 whole numbers. So this is a difficult theorem because it produces solutions to an equation in integers, or a Fantine equation. We have very, very few techniques to produce solutions. And that's, when that happens, you should enjoy it. If you don't like that theorem and you've never seen it before, then probably you wouldn't like number theory, I'm afraid. All right, this leads me to the first permanent member of the Institute for Advanced Studies, who was a number theorist. Well, actually, people may immediately jump up, what about Hermann Weyl, who certainly was everything, including a number theorist, and I will end with Hermann Weyl and drop him for now. Seagull, there's no question, he was a number theorist. He also worked in celestial mechanics. He was a great mathematician, there's no question about that, but I think foremost a number theorist. And one of his great efforts was to understand the general quadratic equation of this type. He wanted to generalize this theorem to all quadratic forms, meaning all expressions like this in any number of variables over any number field, but we'll stick here just to the whole numbers as I have. So he gave a complete generalization. I want to say a word about what this generalization is. It's called his mass formula. In fact, he apologizes at the beginning of his big paper on this, saying, how can people in the 20th century still be talking about quadratic equations? Surely the Babylonians solved all these problems. But over the integers, even quadratic equations are extremely difficult. You saw that question of Ramanujan. Even today, we don't know how to solve it, completely resolve it. Anyway, his mass formula has all the features of this local to global in the sense that it's got one caveat that I want to explain. So he wants to ask not just whether you can represent M by F, but whether he wants to give you actually a count of how many solutions there are. Actually tell you how many ways you can write M as a sum, or N as a sum of 3 squares, which Gauss, of course, was able to give you, by the way. So in general, he is able to answer this, but there's this caveat as follows. The total number of representations of a given integer M by the form that you're staring at, F, let's call it F1, together with, so you have to, unfortunately, in general, throw in some other forms, I'll call them F2 up to FH, which look exactly like F1 from some point of view. So they are called in the same genus. So you have to throw in these other forms, and if you keep all these forms, and I'll show you in an example here in a second, together, this is the nature of the maths formula, then in fact the number of representations of M by the totality of these forms, in some weighted average, is in fact given by just local congruence considerations. So and a very important thing that enters in his work is let's count the number of solutions to the equation. When we're solving things over the integers, you should view it as hard. It is hard. But when you're solving it modulo, in arithmetic modulo 2, there are only finitely many possibilities, and there's usually a structure, which we'll return to in a second. So these numbers should be, and they are, easily calculable. The number of ways of writing Q by F, as it turns out, it doesn't matter if you're working with F1 or F2 up to FH. You count the number of solutions here, modulo q, and that's a finite number. And you analyze those numbers in a way that he explained in this mass formula, and then you get the total number of representations. So he was able to generalize this theory in this mass formula in a remarkable piece of work, which was done more or less around his first visit to the Institute, I believe. Though he announced it seems to me, in a book in Tata Lectures in India. And he also discovered, part of this was understood before him, that what's special about Gauss's problem here with the sum of 3 squares, and Lagrange's case of the sum of 4 squares, is that in those cases there are no partners. You're in a miraculous situation. You don't need to append these other fellows F2 up to Fh, and so you do have a local to global principle. But of course Ramanujan, I don't know if he knew this or not, because he was before this time, had chosen one in which there is a partner. And that's why the pattern is that much more tricky. And so Ramanujan has exceptions to his list. Remember the odd numbers, now we can go back to Ramanujan. When he wrote following numbers obviously not represented by x1 squared plus x2 squared plus 10x3 squared, those numbers all have congruential obstructions, and nobody else does, and every other number should be represented, yet he listed 16 exceptions, and somebody else found 2 more. There were 18 exceptions. Of course, according to Siegel's work, this guy will have to make up where the other guy didn't do it, and it absolutely does. If you check, 3 was the first exception in Ramanujan's list. It doesn't take much to see how to put 3 in terms of F2 by choosing x1, x2, and x3. So Siegel's work, unfortunately, doesn't solve Ramanujan's problem, because it only tells you what happens where each one represents. On the other hand, his theory has become very important, and the developments that are very current. So just to show you what we understand today, and this theorem is really coming out of the Institute a few years ago. Ono and Soundararajan, 2 young guys who were at the Institute. Now let me explain. My brackets means not their lifespan. It doesn't mean, maybe it's the important part of their lifespan. It's their lifespan in the Institute. And it's their lifespan in the Institute in their most recent visit. That will be the consistent notation throughout. So this was, because there are people who've had multiple visits. If I get to someone like Sarah, who I'll mention later, it seems like I would take a whole page to list these visits as a member. All right, so they say if you assume something, which I'll return to, something called the grand Riemann hypothesis, some big conjecture that we all believe, then in fact we can answer Ramanujan's question. That biggest one I wrote down on the first slide is the last exception. But we don't know that. However, we do know something almost as strong. Henryk Ivanic, whose most recent visit was in 1999, made a major advance, and based on that, Duke and Schulze-Pilote proved the following, that in Ramanujan's list, there are only finitely many exceptions. It's quite a remarkable theorem, but it is not effective. Their method of proof, and by the way, whenever you hear not effective, there's one guy who comes into my mind, it's Siegel. They use the theorem of Siegel, which has this feature. He was the master of non-effective. It has a feature which says the following. In fact, if you pushed this proof further, I've never done it, but you could certainly do it, you would be able to show that Ramanujan's form represents exactly the numbers that we think it does, save for one exception. There is no exception, because there is no exception to this big conjecture. But if you found that exception, you would answer, you would disprove that theorem, and you would answer the question of Ramanujan. So don't expect to find the exception, and so the subject sits there as solved in the sense that we do know every sufficiently large number behaves nicely in this local to global principle, but we don't know what sufficiently large means. Philosophically frightening. All right, so that's the status of the Ramanujan's first question, and Siegel was certainly a major player there. Let me return to Ramanujan a second and explain his second conjecture, where it came from, what it's about. Euler and then Ramanujan, these two certainly loved this sort of thing. If you wanted to understand a sequence of numbers an, I give you a sequence of numbers an, one way to try and understand it is look for patterns with an. Another way, given that people like functions and calculus, and something else that I'm turning to, automorphic functions, how about forming what I'll call a generating function, or what is called a generating function, the series a and q to the n, as a function of the variable q. So you could think of q as real. I prefer in a moment to think of q as complex. So the function f has its, this could be formal as well, but if it really is a function of q, this would be its Taylor expansion. So f knows about the an's. The an's determine the f. ABF has some remarkable properties that we can't see in the ANs, and that would be a way to study and see some remarkable identities. And that was what Ramanujan loved and Euler loved. They were able to prove all sorts of identities by manipulating series once they found that F had some extra property. I mean, if I just write the series A and Q to the N, I don't know anything about F, but perhaps I can show something about F. So this function that I just put on the first slide for you, delta of Q, actually has such properties, and this wasn't due to Ramanujan. It's actually goes back, as far as I can tell, firstly to Jacobi, who was shortly after Gauss. And that is, if you take that product that we wrote down, The transformation property is a little hard to write down in a variable q, absolute value q less than 1, because then logarithms would come out. So we write q as e to the 2 pi I z. The z variable is more natural. So this is just a change of variable, but now it's very important, and this will be important for me. If q is of absolute value less than 1, then the variable z is a complex number whose imaginary part is positive, and we call that the complex upper half plane. And in the variable z, Jacobi found a remarkable thing about this, where if you make the ANs the tau's of Riemannian, the tau's that he asked the question about their size, that this function at a transform point, so this is quite a complicated expression, AZ plus B over CZ plus D, where A, B, C, D are whole numbers, and they're AD minus BC is 1. It turns out that these transformations of determinant 1, as what that is, this point will again be an upper half plane, and what this says, remarkably, is the function delta at this point equals the function delta at the transform point times something which I'll ignore, although the 12 there, of course, is related to the 11 over 2 in his conjecture. Well, you've all seen this because you all came here only by invitation. So this is what your picture on your invitation really is, I think. It is actually the upper plane transformed back into the disk, but not by this transformation log, but by another transformation, which is a better one, after which this particular area here is not, there's a subgroup of index 6, so there's some subset of these A, B, C, Ds, which are almost all of them, and such that if you move delta over into this situation, the value of the function here will equal the value of the function essentially reflected in the sides of this, what's called hyperbolic triangle. So that picture is a picture relevant for my talk, certainly. And this object here is called the modular form. And there are many, many proofs since. Jacobi's is quite beautiful. There are short proofs. There are longer proofs. Satir gave quite a long proof using the index theorem. There are proofs using physics, using functional determinants. This is a very fundamental fact that has a remarkable transformation property. And that, of course, Riemannian knew, and that's why he was interested in that function. All right, now to understand Riemannian's second problem, which was the size of the tau's, we turn to not the second permanent member in number theory at the Institute, but one a little later, André Weil. So he was here from 58 to 98. And he, in 1948, wrote an absolutely beautiful elementary paper, which I'm going to go through very briefly here with you, which is about generating functions and is bringing in a generating function that's very important to this lecture, a zeta function. So firstly, he was interested, as we all are, let's get rid of these quadratics. We're not just going to study quadratic equations. Let's take any equation. I'll stick to one equation. So it's important here, I want to be at least a little bit honest, that we count the solutions not as before, just with the coordinates, but we count them projectively. So I'm going to make an equation. So this is a polynomial in n plus 1 variables, which is homogeneous, meaning it's a sum of terms where the x's are to powers and the sums of the powers are fixed degree. Another way of saying that is if I put f of lambda times that point, where lambda is a scalar, it'll be lambda to some fixed power times f of the point. So, of course, if I have a point at which f is 0, then f of lambda of f will still be 0. So I really should count projectively, but that's a technical thing. All right, so you take an arbitrary equation or system of equations, and you try to count the number of solutions to that modulo q. That was relevant in Siegel's formula, and it's certainly relevant in any kind of number theory. The philosophy here is this. It is extremely difficult to understand the solutions of equations over integers. That is one of our aims. That's called the Fantine Equation. And that is hard, and as I said, it's very difficult to produce integer solutions. One thing we can do is look at things modulo q in arithmetic mod q, and then things become perhaps more structured and easier to understand, and that's the philosophy here. Let's count the number of local solutions, and perhaps the local data will give us information. We saw how it led to impossibility of solving. Perhaps it would even do more. So what's the ultimate in that kind of study? So this is what Weil was looking at. And he counts the solutions first in congruences, and he notes follows from something called the Chinese remainder theorem, that if m1 and n1 have no common factors, and you look at arithmetic modulo m1 times n1, it's basically arithmetic modulo m1 and n1 independently. So you quickly reduce to the case where the integers are what are called relatively prime, and hence are prime powers. So when studying this equation modulo p to the r, well, if you like generating functions, you might try to count how many solutions are there to that equation, modulo p to the r. Let's fix p now, and let's r vary, and see if there's some formula. That is a very good thing to do, but it's the wrong thing to do. And it's the wrong thing to do. Weil understood this, following a very beautiful thesis of E. Artin, 1923, who seems to be my first distinguished character, who was not a member at the Institute. The guy's only distinguished in this lecture by not being a member, because that makes him unique. Yeah, all the big contributions, as you will see, except for a few, are either by members or, well, by members. Now, what Weil uses of following R10 is, if we look at the numbers modulo p, the residues, remainders, 0, 1, 2 up to p minus 1, and do arithmetic modulo p, if p is a prime, there's something very special about those set of numbers, is you can add them, you can multiply them, that we understood, but you can also divide as long as you're not 0. And that characterizes being a prime. So if I'm looking at the number of solutions here in arithmetic modulo p, instead of looking modulo p squared, which was what Seagull was doing, let's look at the number of solutions somewhere else. And as I say, this was a very clever step. You might want to, your knee-jerk reaction is to make it modulo p squared. But this happens to be better for reasons that will become clear, and that's also fundamental. So I ask you here to just believe me that for each r greater than or equal to 1, for r equals 1 there's no problem, but for each r greater than 1, there's only one field, finite field with p to the r elements. Okay? And that's where I will look for solutions. So I will let r go not in remainders modulo p to the r, but rather how many solutions are there to this equation that we started out with modulo p to the r, and in particular how do they vary with the variable r. So now there's an infinite set of numbers, and is there some conspiracy? Are they related? Maybe there's some recursion relation between r plus m and r. That's what one is looking for. Symmetry is in the title of this lecture. The way to study this is certainly using something called Galois theory, but I'm only going to tell you what's true and not why it's true, I'm afraid. So symmetry is very important in this analysis. So he formed a generating function, just like Euler and people like that before him. You sum the number of solutions, p is fixed, our f is fixed, we call it a variety, that's fixed, and we sum the number of solutions of the field with p to the r elements over r times t to r. We make this formal sum. We're clever, we exponentiate that for reasons I won't explain. It'll be clear in a second. And we form that function of t, of the variable t. And they, based on calculating some examples, well, based on, firstly, something he understood very well, work of Emil Artin in the case that this was a one-dimensional set, the set of solutions, which at that point was well understood. He looked at some examples, which are quite simple ones, from which he made just absolutely beautiful conjectures, general ones, which, as you'll see, turned out to be correct. His conjectures are the following three statements. The function as a function of t, which this generating function, is actually a very simple object. It's a rational function. It's a ratio of two polynomials. If you don't like that, there's a formula for n of r, p is fixed here, and f is fixed. I'm just looking at the variation in r. There's a formula for the number of solutions in the field with p to the r elements, given in a finite amount of data. In other words, there are n complex numbers, beta j, and n m complex numbers, alpha k, such that the number of solutions is simply beta j to the r summed and alpha k to the r summed. So there's a finite amount of data which determines the complete story. There's nothing better than that. That means those numbers are what you want to understand, because they tell you everything about how many solutions there are. Not only did he conjecture that's rational and show it is so in a few simple examples, but he showed that, just like we were talking before, if a generating function has a relation, you'll understand it much better. He discovered, or he conjectured, that the value of the function at t, now it's a function of t which is rational, it's defined everywhere, is the same as the function up to some factor at 1 over t times p to the n minus 1. And then, more generally, and this is the Riemann hypothesis appearing again, this is the analog of the Riemann hypothesis, he conjectured where the zeros of this function lie. Now, I've taken only one equation. If you had several equations, then you would have zeros and poles, but I've stuck to the simplest situation. As far as the zeros, and in that example, he knew very well. One understands much more easily where the poles are. In any event, these are the key numbers, and understanding their size, where they lie, in this case, their absolute value. I hope by now you're recognizing that at least at some numerological level, this looks like Ramanujan. But he formed this generating function and made some remarkable conjectures about it. That's his 48 paper, based on some very simple examples. And I should say that he also understood the relation to the topology of the manifold of zero sets over the complex numbers. Quite remarkable that he foresaw all that from his few examples and his knowledge of what goes on in one dimension. So one was first proved by Dwork, who was a member. This was proved long before 83. He was a member in 83, 84 most recently. 1 and 2 were proved by Grothe and Dieck, who invented a theory to linearize this problem, a cohomology theory, which is very powerful. And the hardest part, using Grothe and Dieck's theory and using extra symmetry, monodromy symmetry, was proved by Berlin, who's a member here today, but I think, according to my information, came in 84. So these conjectures were solved, not so soon after, but eventually, I think this was 1974, they were all resolved. Grothe and Dieck, as I said, there will be someone who's very distinguished by never having been a member, according to my information. By the way, if you want to find this information, go to the website, go to past members, and they had them alphabetically. And you can see exactly, according to that list, Grothendieck was never a member. Okay. Now, that is sort of a marvelous thing. When I talk about the Riemann hypothesis, the real one, you'll see where Weil was coming from in a second. You'll see the analogs of these three things. But in the meantime, this was a great achievement about counting solutions over finite fields, as they are called, and the structure of this generating function called the Zeta function. It is quite remarkable that that theory, this theorem, and especially the third part proved by Deligne, leads to a proof of that second question of Ramanujan about the size of power of P. You saw the way I stated it and the way Ramanujan stated it about the size of the roots. That, of course, looks the same, but of course, the passage from there to there is not something elementary. It was, this kind of passage was first seen by Eichler, not in 64. I just keep on repeating. It looks like he did it in 64. This is when he visited. Eichler was the first to see this connection between this kind of problem of Ramanujan and solving equations over finite fields. So this is the theory of modular forms that I mentioned. Ramanujan was interested in delta because it's a modular form. Eichler developed that theory. Shimura further in a very important work. He was most recently a member in 82 to 84. It is not so well known, but Sato, Mikhail Sato, was a member here in 1960 and was highly influenced by André Weil and was interested in this reduction in particular. And his reduction was written up by the member Ihara in an Annals paper in 66. It's complicated. A complete treatment of the whole story was done by Deligne. So this reduction is by no means easy, but what I'm telling you is one can use part 3 as the main beef to prove Ramanujan's conjecture. So it's interesting, the second conjecture, which actually I think looks, if you first see it, much more difficult, is solved, but the first problem about the quadratic form remains unsolved. All right, by the way, the first question I raised two problems of Ramanujan, raised two questions. One was a multiplicativity, that tau of m times tau of n is tau of mn, if m and n are relatively prime. That was solved very quickly after Ramanujan posed it by Mordell. So Ramanujan's second questions are completely understood. All right, I've mentioned the Riemann hypothesis a few times. What is it? The real Riemann hypothesis is due to Riemann. This is much older, and what this is about a generating function, just like the generating function for counting solutions we varied R. Now we're going to get really ambitious. Riemann is earlier, he's much more ambitious. He varies the prime. So we were fixing P and we were letting R vary. Now I'm going to vary P. This is a much more difficult thing to understand. In any event, Riemann introduced some properties of this function in 1859 paper, where he looked at the series 1 over n to the minus s. And if you've never seen this, that's 1 minus s plus 2 to the minus s. S is big, say. And now, if I multiply this infinite product of, if I take 1 minus 2 to the minus s plus 2 squared to the minus 2 minus s and so on, and here 1 minus 3, an infinite sum like this for each prime factor, and multiply those all together, think what I'll get. I'll get something out of the first bracket, something out of the second bracket, and so on. One of my daughters says you bust open the brackets and you get sums over n to the minus s. If you open it all up, that fact that you just get every integer once and only once is just a statement that every integer is uniquely factorizable into primes and their powers, order not important. So we have an identity that this function is related to the primes, and this is due to Euler. And the fact that this function is related to the primes in that way probably tells me that if I understood by this generating function philosophy, say if this function were rational, wouldn't that be nice? Then I would understand the properties of primes through this function. And Riemann pointed to the same three things that Weil was pointing out to much later. Number one, he showed you could make sense of this function for all numbers s. That would be the analog of, in the Weil situation, of showing functions rational. He had an entire function, say, for a simple pole. He showed that. He showed that at s and 1 minus s, they're related. In the other case, we had a different variable. It was a t and 1 over p to the n minus 1 times t. So he showed this fact that it makes sense for all s. It's got a functional equation. And he posed a problem which is much harder than what we don't know on the first question of Ramanujan. Where are zeros? And he even computed the first few zeros himself, and he conjectured they're all on the line and a half, and I hope you recognize that that's the analog of all the zeros of that rational function lying on a circle. So I think it's kind of obvious where Weil was coming from. Riemann's long before Weil. So this is the generating function for the primes. Certainly people at the Institute have worked on this very hard and elsewhere. Unfortunately, that remains unsolved. You can go to the Clay Math Institute. They're offering $1 million if you solve that problem. That's your only motivation. Don't work on it. You can also see a beautiful description of what the problem is by Enrico Bombieri. And I've actually written an updated account of the problem, which will be on their website also. Now, I mentioned Weil. Selberg was a member before Weil, and he's still well and alive, and smiling here in the front. He worked certainly on this very difficult problem and things around it, as did Bombieri, two members here. And even though I should say this problem is very difficult, and perhaps the best results on it have come out of here, and let me describe a couple of them. And the first one is due to Selberg. On this problem of where the zeros are, he showed that for this generating function, while he can't show that all the zeros are on the line and a half, it turns out this is not a rational function. There are infinitely many zeros, and he proved a positive proportion of the zeros are on the line. Now, if I may say so, the result itself is perhaps not as interesting as other problems, like the second one, but the techniques developed by Selberg to prove this are by far the most fundamental tools we have today. It is often the case that when somebody makes progress, the tools are more important than the result, and this, I think, fits into that category. But he may argue with me, I don't know. Anyway, the tools are marvelous, and in fact, the tools that he developed there are used to resolve, in part, that result that there are only finitely many exceptions to Riemann-Huygens' first problem. So these things are highly interwoven in the end. So it's an extremely important achievement of Selberg, who was a member in 49. Bombieri has sacrificed the proof. Well, I don't think he's given up, but suppose you say, let's not prove it, let's prove something a little weaker. So he's proved extremely important approximations to the Riemann hypothesis, not just for the Riemann zeta function, but for families called Dirichlet L functions or zeta functions, in which he shows in a very sharp and strong form almost all the zeros are on the line and a half. That's not quite, but I think a good enough approximation to this statement. But most importantly, and this people don't seem to be aware of, which is why I want to highlight this point, this kind of result, this kind of approximation, can often serve as a complete substitute for this Riemann hypothesis. So even though Clay will offer you $1 million for this, we're interested in this not only because it's a fundamental truth, because there must be thousands and thousands of results which are in the literature which assume the Riemann hypothesis then. It's a truth that we're really eager to know because it's powerful. And so instead of summiting the mountain, Bombieri goes around the mountain. He gives you a tool which will allow you to often achieve the consequence without knowing the Riemann hypothesis. So these approximations are not approximations that are just, oh, well, that's more or less 50, some percentage. They actually replace the Riemann hypothesis in certain applications. All right, let's mix everything together. I have 10 minutes to do some mixing here. And this is again Weil, Hasse and Weil. Let's get back to our equation V, which is our homogeneous equation, which we have now satisfied. We understand how to count the number of solutions modulo p and p to the r when r varies. But what happens if we vary p? Because that's rarely going to be the ultimate zeta function. So let p be large, otherwise when I look at this equation modulo p, something funny may happen, and one has to worry about that. But we have for each prime p, for our equation, we have a zeta function that they gave us, that we now know is a rational function. We even know where its roots are, zpft. That's why I kept the p. So our main object we start off with is our equation. We want to study solutions to this equation. It's, as I keep on saying, difficult to study it over the rationals or over the integers. But let's study it mod p, and let's put them all together like Riemann did, one factor for each prime. So this is really as Nick Katz has put it in a paper, I really like his expression, this is all the local Fantine information that V has to offer. There is no more local information, incongruences and fields over finite fields that it has to offer. We put them all together into the mother generating function, if you wish, which is a product over all primes of these local factors. It's not difficult to see that this product makes sense for S is large. And they, again, with his examples that he was looking at in that same paper, or maybe a year later, asked, quite naturally, and I guess Hasse maybe before him, do these functions make sense for all S? I mean, at this point, everybody here in the audience would ask these questions, since I've got the same 1, 2, 3. 1, extend this to make sense for all S. Secondly, does it satisfy a functional equation? And thirdly, where are the zeros and poles of this function? Well, we know this is going to be pretty tough because it's going to be at least as hard as the Riemann hypothesis for the simplest of these functions. But maybe 1 and 2 is something that we can solve. And they computed these in few examples and was able to show this is perfectly true, that you can make sense of this for all S, and it is a functional equation. Well, in general, we have very few results. There's only one case where we know this handsomely. And that's a case of the next simplest equation beyond the quadratic equation. And that's an equation called an elliptic curve. Now, I'm going to write the equation not in homogeneous form because that's the easiest way to present it and look at it. So we're going to look at an equation y squared equals a cubic. That's the next most complicated equation, and it's studied precisely because one can compute a lot with this. There's a lot of algebra and technology that you can associate with this situation. So we look at the equation y squared equals x cubed plus x. Let's say a and b are integers, and of course they must be such that this thing is not degenerating. Okay, I should count the solutions projectively. I do. And I form this Satisfies Zeta function, this big generating function, which is now trying to measure how things vary as I look at the solutions modulo P and fields above it, and then as the prime varies. So we form this and ask question 1 and 2. And quite remarkably, we know the answer in this case. And this was a remarkable achievement 10 years ago. It's about 10 years ago, and it was when Wiles became, I guess, a longer-term member. He's been a member since 95 here, part-time member. He proved that 1 and 2 are true. Actually, here I didn't do the most general elliptic curve. The complete solution is due to his co-worker, Taylor, and his students. Taylor was also his student, Dimond, Conrad, and another fellow, Bruel. So they were able to complete the story, but the remarkable thing is we know the answer to We's question for an elliptic curve. And that is a major achievement, and that deserves great celebration. The fact that it implies Fermat's last theorem, that's just the cherry on top. In fact, that it implies Fermat's last theorem is quite remarkable. I should say this is essentially equivalent to his proof of what's called the Shimura-Taniyama-Wei conjecture, which relates elliptic curves to modular forms in a more geometric way, but it's equivalent to the statement when understood properly. And the fact that that implies Fermat's last theorem was already known before Wiles, and that was a remarkable insight of Frey, based on earlier ideas of Serre, which he had to reduce it to in work of Ribbett. Serre's most recent visit was 00. It's wrong on the list. I was here and he visited, but they don't have him as coming. I don't know why. Maybe he was paid less than usual. All right. Now, this is just a special case of an elliptic curve. We started with quadratic forms. Elliptic curves understood. How about the general case as far as P varies? And this is really where a lot of work is being done. It's a very exciting area. While we have no idea how to prove this in general, we know where to look. We know where to look. And I want to just say that and explain to you some features with that. The answer is not going to be anymore in the upper half plane where Ramanujan and people like that were working. You take a general equation. Unfortunately, it's not enough to just look at 2x2 matrices. You have to replace the upper half plane, that picture that we saw here, with its hyperbolic geometry and its group of rigid motions, by more fancy spaces of geometries and their rigid motions. So you have to replace a hyperbolic plane by a symmetric space, as it's called, which at this point I'll just tell you is a higher dimensional version of the upper half plane, and a group G of motions which preserve this, if you like, in its geometric structure, preserve the geometry. And these other groups are much more complicated groups than just 2x2 matrix groups, and they typically are semi-simple groups. And the idea that you make a generating function, generalization of a modular form, is now some function which satisfies much more some differential equations, and its values at 2 points are related just like they were before, under a group which is like the 2x2 integer matrices, a discrete group. That's the setting in which we believe the answers lie. Well, let me leave that here. This is my last slide. And this has become an absolutely central theme of study at the Institute by many people, and I want to mention a few things here. Firstly, this higher dimensional example in these groups G and the discrete subgroups were studied first, always, by Siegel, who was very interested in quadratic forms, and a little bit more, but still, Siegel and Ray studied this in connection with the quadratic kind of equation that I would put up in connection with, for example, Ramanujan type of problem. So they studied these space orthogonal groups in great detail, Siegel and Ray, but mainly in connection with quadratic forms. A major development was done by Berg, laying down the foundation to study this more generally. So he developed a spectral theory. This is already, one can't live as Wey, I think, put it, Mars had to free us of the ghetto of holomorphic forms. You can't, not every one of these spaces has a complex structure. So one actually has to open to a much bigger theory, spectral theory, and the spectral theory of these spaces was pioneered by Berg, who also developed something that has become one of the most important tools in the subject, the trace formula. So these spectral ideas were developed here with these applications in mind to this understanding these kind of more general problems. The study just of the analysis of symmetric spaces, the harmonic analysis of these symmetric spaces or the groups G of motions and their representations was developed by another member, Harishchandra, from 63 to 83, who almost single-handedly developed all the machinery that one uses, at least first at the real places and then chaotic places. Borel, who was a member here from 57 to 03, developed the foundations of the theory of arithmetic groups, which are absolutely needed in the theory. So I would say Harishchandra and Borel and Berg and Siegel were all developing the soil on which we can plant our trees. And they did it successfully so that we could actually carry this out today and use it. The connection that was so surprising, which I didn't explain at all, between Ramanujan's problem and the Weil conjectures, this geometry of moduli was developed primarily by Shimura and Deligne, who I've mentioned before. But I would mention, amongst all and above all, Langlands. He was kind to me, so I'm going to be super kind to him. Above all, Langlands, whose work on this has changed the subject in a very dramatic way. Most importantly, after studying Selberg's work on what are the analytic continuation of Eisenstein series, which are the sort of workhorse of the subject and of the trace formula, he saw a unifying theme. And that's always what we really hang on to, because the subject is very complicated, and everybody is calculating their own examples, and what's the theme? Where are we going? Langland saw this through the theory of Eisenstein series, something called functoriality. I can't explain it to you here now at all, but on the 100th anniversary of the Institute, there'll be some young guy here who I guarantee you will be explaining to you what functoriality is and what great achievements have been done. His unifying theme unifies all this, gives us the landscape on which this question is going to be answered. We know where to look for the answers, we just don't know how to answer them now, and there are serious technical difficulties. So let me end with Hermann Weil. Hermann Weil was perhaps one of the earliest members here, as far as I can see. He is a mathematician who did everything. So he obviously did number theory, and in fact I can name for you quite spectacular theorems of his. He worked on the Riemann Zeta function, developed Weil sums, which became the bread and butter for Hardy and Littlewood to study many, many problems. He even wrote the first, I think, Princeton series book in existence, which is a book on algebraic numbers. He was even interested in those, and some people have told me they like that book very much. So there's no question that maybe I should have mentioned him first. However, his impact on this subject, on the subject of representation theory and symmetry, which is what's the theme now, unifying everything, is immeasurable. He is the fellow who understood the representation theory in the 20th century for compact groups and representations, finite dimensional representations of these groups. He wrote down their characters. He single-handedly transformed that subject. And, of course, he was a number theorist, but I think he probably wouldn't call himself a number theorist. Thank you.
Well, thank you very much, Peter. I would like to say, in case I think there are some non-mathematicians here, and if they felt they didn't understand everything, I've been thinking about these things for many decades now, and I have the feeling that I understand nothing in any very serious way. And it also seems to me tremendously important that these notions be taken seriously as a chapter in the history of ideas and their philosophical depth and their historical depth be made clear, I think, to the world at large. And Peter, I think, has done as well as one can do in an hour to explain that. Now, please feel free to ask questions. Would you mind, Peter, repeating the question before you answer it?
Yeah. Yeah. Right. The Ramanujan's problem. Actually, it would be a counterexample to the Riemann hypothesis for Dirichlet L functions. And just to show you how confident we are that there should be no difference between the Dirichlet L functions and the Riemann Zeta function, Hardy, I just noticed this a week ago when I was trying to write this report, has a comment that it will take, he assures you that it will be a week. If somebody proves the Riemann hypothesis for the Riemann Zeta function, within a week a proof will be found for all Dirichlet L functions. I think he's naive, actually, but he assures you. So what I'm saying is, it's certainly, we don't see any difference between these functions. We move to these much fancier functions where it's proved. In fact, if you ask for evidence for the classical Zeta function, one of the great pieces of evidence is the achievements of Deligne, for example, for these Zeta functions. Well, that must have been much clearer than I thought.